Good afternoon, everyone. Just we continue with the bending of beams, and the new topic we learned this week, that is the performance of the beam is not only a function of loads, but also it has to do with the cross-sectional geometry of the beam. So we introduced a important parameter called moment of inertia, and maybe in the next class or next week we would correlate that parameter to the performance of the beam. But for now, what you need to know is, first, given a beam structure, are you able to analyze the variation of internal forces inside the beam? So when we say internal forces, that it has three important parameters. So internal forces in beam, the most important one is shear force, and generally we show that with n of x. So sorry, this is v of x, So X emphasizes the point that the shear force is not constant. The shear force, generally speaking, it does change through the axial direction of the beam. The second important one is the bending moment, and that is represented as m of x. And less importantly, that's the normal force, or n of x, normal force. But mostly we are interested in shear force and bending moment. So once you find the distribution of these internal forces, we are also interested into the cross-sectional parameters. So these are center of gravity, and that is area, and that is first and second moment of inertia. So yesterday we discussed how the second moment of inertia make a difference in performance of the beam, and we learned how to calculate them. So when you are calculating I, that is either a primitive shape like rectangle, circle, triangle, or these are primitive shapes, or it could be a compound shape. A compound shape, I mean, you use your imagination, you can have these primitive shapes combined together to make a primitive compound shape. And for today, we go on with some calculation of moment of inertia. But again, the challenge is to solve a beam, finding the internal forces. So maybe today we spend some more time with analyzing the beam itself. Once you know how to drive the variation of shear force, plot them, and bending moment, calculation of moment of inertia, center of gravity, these are very routine, standard things, shouldn't be challenging as such. All right. Anyone remembers when it comes to finding internal forces? We mentioned there are two techniques. Do you remember those techniques? How do we find them? The first technique goes back to the last week. It was through the free body diagram. And free body diagram is useful when you want to just identify the internal force at one single point. So imagine I give you a beam. This is a beam. And I only ask you, this is a selected point, point D, and can you find out the internal forces at that point? So in another word, I want you to find N of D, B of D, and M of D. With that, the preferred technique is free body diagram. So you cut through that specific point, and making a free body diagram, over there you should be able to find out three internal forces. The second method is method of equation that we started last week and continued this week. The method of equation is different in that it classifies the beam into a number of zones, and how many zones, that is a matter of how loading do change, external loads change. Distributed loads, point loads, if there are variations, you have to split the beam into a number of more zones, and every zone is governed by its external loads. All right. And the next thing is, for each zone, we start from finding W of X. Do you remember what W of X is? I mean the definition. What is W of X? Toby, do you remember? Intensity of load. Yeah. What is the unit? Newton per meter. Yeah. Yeah. So that's a definition. But the variation could be a line, constant, quadratic, right? So W of X terminology, we call this intensity of the load. And then when we say intensity, it means this is not Newton. This is Newton per meter, Newton per area, Newton per volume. In your case, most of the problem you deal with that as a Newton per meter. So in the method of equation, we start with W of X. And then the next step is I find shear force V of X. That is the second step. And the third step is to find out M of X. That is the third step. And how do we go from 1 to 3? That is by method of equation. Method of equation says dV over dx is equal to W of X. Just by integrating that equation, as an input, you have W of X. So you input W of X, integrate, and that gives you V of X. Then the next step is, now you have V of X, input that to the next equation, which is derivative of bending moment with respect to the X is equal to V of X. So this, as an input, has shear force, and after integration, what you achieve is bending moment. All right, so that was a very concise summary of where we stand now. And if you just 10%, 20% to 100% understood what I said, the rest should be easy, because doing these exercises, we iterate and try to understand them better. All right, let me get this interesting problem. Maybe why this is interesting, because the support at the left hand side, maybe you haven't seen that before, but by induction you should be able to analyze what it does. All right, can you tell me the left hand side, how does it operate? What is so special about the left hand side support? So a support is serving by resisting against the force. What type of resistance does it develop at A? How does it? I mean, it offers resistance toward the horizontal movement, but maybe that horizontal movement is irrelevant because we don't have any horizontal force. Agree? Yes? All right. What about the, does it offer vertical resistance to vertical motion? Well, you see there are two gaps at the top and bottom. So that means this is free to move vertically, right? So that, I would classify this as a cantilever, but this is not cantilever. Why it's not cantilever? Because it does not resist against the vertical, and horizontally, we don't have any horizontal force. So basically, A is only offering resistance toward what? Rotation. So it only develops bending moment. It resists against the rotation. Can you see that? Yeah? Or in that sense, all these was to understand how to make the free body diagram after releasing that. So you release A, and you realize that AX is irrelevant, AY is 0, and MA, that is something you have to include in your free body diagram. Okay, so first thing first, before I can plot the v of x, I need to solve the reactions. So I can do this in a number of ways, but an easy way is I'm gonna release BD. So let's release BD. So that would end up with a member BD, and BD has an external force at D, and it has a vertical reaction in the middle, and just one resistance here. All right, so I think that is P, and if I take moment of rotation with respect to the B equal to 0, that gives me C of y that is equal to 2p. And if I take moment of rotation with respect to the d equal to 0, moment of rotation with respect to d equal to 0, that gives me b of y is equal to p. So that is how this force is developed inside the reaction and the connecting point B. Now I have to reverse this force, and okay, now I think we can make the free body diagram of BA. So BA at point B, I have to reverse that force. So that force being reversed is a force of P applied here, and force P applied here. And at the end, you only are going to have a bending moment, M. So this is P, that is P. And then, I mean, P is a given value. It's not a unknown, it's a given value. What you want to find is MA. So letters, that is point A, that is point B. So let me take moment of forces with respect to point B equal to 0. That is P times A, and that makes a positive rotation, minus MA is equal to 0. Therefore, MA is equal to PA. Now, from this point, it should be straightforward to plot the shear force diagram and bending moment diagram. So how do we do that? Well, first of all, how many zones do you identify here? How many zones? How many regimes? Just AB. With AB, how many zones do you identify? Between A to the middle, the load doesn't change. Suddenly, you have a discontinuous shear, right? And between P and B, nothing changes. So the two zones is enough to describe AB, isn't it? Two forces. But if you want to consider the entire beam, the free body diagram for the entire beam looks like this one. That is this is point A, that is point B, and that is point D. So you want to decide, and then that is point C. Deciding regarding the number of zones, that is dictated by how many external load are there. So in that sense, now we don't care about B. B is put together, that's an internal force. With the internal force, we don't care. The only thing we know is at point B, what type of internal force develops at B? It's a very important question. I want everyone to think. Maybe it's worth if you think 5 minutes and tell me what is so special about point B. If this is a beam, that's not a normal beam. It's a compound beam. This is like you have connected two beams together. But what is special about point B is point B cannot take any rotation. So you know that at point B, the moment of the bending moment is equal to 0. Is that agreeable? Point B is a hinge. It cannot, I mean, it's frictionless. It cannot take any bending moment. So we know that at point B, the bending moment is equal to 0. All right. So now I can identify how many zones is needed here. So one zone between here to there, and also between that point load and point B, I consider one zone simply because I know here the 0 bending moment. So 1, 2, 3, 4 zones I define. So that is zone number 1, zone number 2, zone number 3, and this is zone number 3. Okay. Maybe we can start from the other side to this side. All right. I mean, this is up to you whether you want to get the x-axis from right to left or left to right. And the reason, yeah, well, nothing wrong with do it in a orthodox way. We just keep the x-axis going from A to D. So starting with zone A, zone 1. So X is between 0 to A. And what can you tell me about shear force at A? What is shear force at A? Yeah, the shear force is zero, isn't it? You don't have any shear force at A. Because A is free to move vertically, it cannot resist any shear force. So shear force at A is equal to zero. And what can you tell me regarding the W of X in the first zone? What is distributed load? In the first zone, what is distributed load? I don't see any distributed load, do you? So that Wx is zero. All right, if W of X is zero, that would tell me what? It says dV over dx is equal to W of X equal to zero. And as such, when I integrate both sides, I find out that let's call this middle point something like A, B, C, D, E. Right, so this is point E. All right, Leon, what you missed, let me just quickly explain. Here we have what is called a compound beam. Compound, you can combine a number of beams together, pin them or somehow weld them together and make it one single beam. All right, so here we have AB as one beam and BD as another beam. So now they are being pinned together at point B, right? And so in these cases, what is so special about point B? Point B is that P cannot take any bending moment. So I know that at that particular point, M of B is equal to zero, right? And regarding A is a very special support. It is free to go up and down. It's not like cantilever. It's free to slide vertically. Horizontally, it doesn't have any load, horizontal load, so there is no reaction. It only can take a bending moment, MA. So we solved that beam, found all the reactions, and now we decided to have 4 different zones to describe the plot. So this is zone number 4. Okay, and can you see how we concluded VA is equal to 0? Because A is free to slide, it can't take any shear. VA is 0, right? And in the first zone, because W is 0, W of X is 0, if you integrate, you find out that VA is equal to VE. VA is equal to VE is equal to 0. So if I want to plot that one, so the first graph you plot, that is V of X. For the first zone, the shear force is 0. Shear force is 0, no shear force. All right, and all right, now let's plot M of X for the first zone. That is dm over dx is equal to V of X. So this is equal to V of X is equal to 0. And therefore, that gives me M of X minus M of A. That is equal to 0. So I conclude that Mx is constant in the first zone, and the magnitude is equal to PA. So So in the first zone, the bending moment, m of x, that is equal to PA. Enough? Okay. Now, what happens at point E? At point E, you have a discontinuous shear force with a magnitude of P. So I can conclude that in the second zone, the shear force drops. How much it drops? By the magnitude of P. So there's a discontinuity here. How large is that discontinuity? That is equal to minus P. And it doesn't change between point E and B. Why it doesn't change? Because W of x in this zone is 0. When W of x is 0, its integral is constant. All right, now that I know in the second zone, it's zone number 2, V of x is equal to minus P. So therefore, m of x minus m of E, that is equal to integral of minus P dx. And that is m of x minus PA is equal to minus px. And then m of x in the second zone, that is equal to minus p of x plus pa. So it means the bending moment changes linearly in a decreasing way. And to find out bending moment at point B, I have to plug x equal to a, and that is 0. So from here, the bending moment reduces to 0. Okay, so we took care of the first zone, second zone. Now let's go to the third zone. Okay, third zone. Starting with, I bring the coordinate system at B, and that is x changing between 0 to a. And what is W of x in the third zone? No W of x, that's 0, right? So therefore, V of x minus V of B, that is equal to 0. So again, my V of x is equal to V of B, and that is equal to minus P. Right? So it keeps going here. And then just look at this. We found m of B equal to 0. Does it comply with the physical limitation of the beam? The physical limitation of beam is at point B, you have a hinge, it cannot take a bending moment. So at point B, you expected to have 0 bending moment, and now this is 0. That fits the expectation. And right. So if I want to find variation of bending moment between B and C, so this is between B to C. So that is m of x minus m of B is equal to integral of minus p dx. And this one is 0. So that is m of x is equal to minus px. So minus px, that is 0 at here. But then when you get to the point C, it becomes minus PA. So it goes to minus PA. And then here I have a discontinuity in the discontinuity in shear. So that discontinuity from minus B brings that to plus P, which is 2P. 2P is the magnitude of the shear force here. So therefore, that point is plus P. And between C and D, the W of X is 0. Therefore, the shear remains constant. And suddenly, this one is P. So that one brings that to 0. So just starting from 0, going back to minus P, constant, going to the plus P, constant, coming back to 0. And as far as the bending moment is concerned, in the fourth zone, zone number 4, M of X is equal to Px. Yep, Px. So Px minus P. So at the beginning, that is x equal to 0, this is minus P. And at x equal to A, so this is PA. Come back to 0 here. All right, so this is an example of a composite beam. You have hinged two beams together. The right-hand side is like a seesaw. You have a support in the middle. Two forces are acting vertically down. The support will take double the force upward. And on the left-hand side, you have something like a cantilever, but the cantilever which cannot take a vertical resistance. And these are the variation of the shear force bending moment. All we did, we divided that composite beams into 4 zones. For each zone, use the method of equation to derive the V of X and M of X. Any questions?
So the bending moment always be equal to shear force.
The bending moment always.
The graph bending moment does always be equal of the shear force.
It is, but at the same time, if there are point loads, they would act as a discontinuity. I mean, because we have two shear forces here, there should be two discontinuity. If you look at the shear diagram, you see two discontinuity, right? One is minus P at point E, one is 2P at point C. These are the discontinuity. And is there any discontinuity in the bending moment? That is only at the beginning. At the beginning, you have a moment A, which is equal to PA. That serves like a discontinuity, and everything else is continuous. Okay, so going back to the practice, to the worksheet, and here you tell me which problem you want us to solve. And I mean, this is an interesting problem. This has a discontinuity in shear and bending. Can you tell me how bending discontinuity comes here? Do you remember in the early weeks, we had a topic regarding changing the line of action of a force. So if I want to transfer this force from here and bring it here, what happens? I have to pay a penalty because the line of action is changing. I bring that one here, the penalty is this multiplied by that distance, that makes a bending moment. All right? So just let me give you a hint. If you want to solve this yourself, you are more than welcome. But just wait until I give you the hint. so you can solve it yourself. All right, so how do I solve this one? Well, I need to find out the reactions, so we know how to find the reaction. I hope everyone knows how to find the reactions. So this is one force here. That is a roller. The roller would take a vertical load, and this pin is taking offering two resistances. All right. What should I do with that 100 Newton here? The 100 Newton, if I want to shift that, if I want to transfer that to point C, it's an illegal operation because a vector can be transferred along its line of action. But if you want to change the line of action, you have to pay a penalty. So let's pay the penalty and shift that force from, which is off center. I want to bring that to point C. I bring that to point C, but then the penalty I pay is a bending moment, which is equal to 100 times the distance is 0.25. That is 25 kilonewton meter. So that's a external bending acting here, which makes your shear bending moment diagram discontinuous at that point. And can you tell me how this force would impact the graphs? So you remember we do 3 graphs. How does this axial force impact the internal forces? So what type of plots we have? We have 3 plots, right? V of x, M of x. What is the third one? N of x, axial force. So that axial force is active between C and B. Left-hand side of the C, there is no axial force, but the right-hand side, you will have axial force. So if you want to plot the N of x versus x, it goes 0 between A to C, and between C and B, you will have a constant axial force. Yes? All right. Who wants this problem to be fully worked out here, or you want to do it yourself? I think the challenging part was this one, but if you want me to solve it, just say it. Solve it? Yes? Okay, let's solve it. All right, so the first thing is to make sure the labels are complete. That is A. This point, let me call that D, point D. And that point is already labeled as C. And this one is B of X. And this one is called B of Y. I mean, I shouldn't have taken this arrow like that. The normal, the default is to assume everything is positive, unless the otherwise is. So that I call this B of X, B of Y, and that one is 100 kilonewton. And that one is M of C. All right, first thing first, how do we find out the reactions? So reactions. To find out the reactions, I take sum of rotation with respect to the A equal to 0. And for that, I get 75 times the arm of rotation is 1. And this is making a negative rotation. And then I have a positive rotation of 25, that is this one. This 100 Newton is passing through A, that won't make any rotation. B of y makes a rotation in a positive direction, that is plus by, and the arm of rotation is 3. And what about bx? Bx passes through A, that makes a 0 rotation, is equal to 0. So from here, I get B of y is equal to 75, take away 25, that is 50, divided by 3. That is 16.167. And this one, B of x, that is equal to 100. And the last one is to find out A of y. So A of y, simply we take sum of the vertical forces equal to 0. That is A of y minus 75 plus 16.67, that is equal to 0. $58. Sorry? Maybe, let me check. 58, yeah, 33, yeah. Is that what we said? Yeah. All right. So now I don't need the detail of the calculation. Just let's keep the magnitude of the reactions. So I want everyone to give this a try and tell me how many zones are identified here. 3. Anyone objects? 3 zones. So the first zone is between A and D. So that is zone number 1. I simply bring everything here. Okay, let's start with zone number 1. That is between XA and XD. These are 0 and 1 meter. So in that zone, okay, that was 16.67, and that was 80 or 50, 58.33. Okay, so sorry, yes, AY, that is 58.33, wasn't it? 58.33. Okay, in the first zone, what is W of x? 0. W of x is 0. And what is V of A? Yes, that is 58.33. And what is M of A? 0. Okay, now we are ready to start solving. That is V of x minus V of A is equal to 0. Therefore, V of x is equal to 58.33. It doesn't change. That's in the first zone. All right. And then M of x minus M of A, that is integral of 58.33 dx, which is equal to 58.33x. And this is 0. So that therefore is equal to M of x. All right. And how do I find M of D? How do I find M of D? Just plugging x equal to 1, that gives me M of D, right? But then the unit is Newton, kilonewton meter. So at this stage, we can plot both V of x and M of x for the first zone, right? So this is constant. And then from 75, if I go down, this is discontinuity, right? So if I go down, it brings me to where? It brings me to 60 minus 16.67. Okay. And then the bending moment starts from 0 and it goes to a positive bending at here, which is equal to 58.33. Okay?
Why did she change to
Because 75 is acting down. So that is discontinuity downward. So initially that is positive 58.33. If you take away 75, you end up with a negative residual. Yeah. So now I think we can continue in the second zone. So in the second zone, let me just get rid of that detailed solution. So in the second zone, this is between D and C. Again, I bring my coordinate system here. So D represents x0 and C represents x equal to 1. And what is W of x here? 0. And regarding V of D, should I take V of D at the left-hand side or V of D at the right-hand side? V of D negative or V of D positive? Positive. This is discontinuity. I mean, forget about the previous zone. Now you are in the second zone. In the second zone, everything is on the right-hand side, not on the left-hand side. Right-hand side, that is after having minus 75 affected. So which number should I put? Should I put 58 or should I put minus 16? Minus 16. Yes? Agree? Agree? Gabriel, can you see why did we took minus 16 instead of 53? So in the second zone, here, right? Should I take that shear number or this shear number? Left hand side or right hand? This is discontinuity here. Should I take off the before or after? after, because now you are in the second zone, right? Forget about everything else order. We are in discontinuity order. So that makes this one v of x minus v of d is equal to integral of 0, which is 0, but v of d is minus 16.67, so therefore v of x is equal to 16.67 kilonewton. All right, and now the next thing is to write the equation for bending moment. So dm over dx, that is equal to v of x, which is equal to minus 16 point, sorry, plus 16.67, and therefore m of x minus m of d, that is equal to integral of 16.67 dx. So m of d, what value should I include for m of d? 5833, right? So that is so therefore m of x is 16.62x plus 5833. And if I plug x equal to 0, that gives me this number. And if I plug x equal to 1, that gives me m of c. M of c is m at x equal to 1, which is these two numbers added together. So that is 75. So here, by going from point B to C, I mean this one, that is doesn't change. I think I made a mistake here, and no. Yeah, v of x minus minus is positive. You bring it to the right hand side, that becomes positive. So and likewise, this is negative, 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 and one more negative here. And here I have equal to 58.33 minus 16.67, 40. All right, and now in the last zone, we don't have any changes of the shear force. It comes to the same number here, but then the reaction brings that one to 0 here. The reaction is 16 point. Yep. And so if in the third zone, I have a negative so this is a discontinued, bring that 25 down. So that bring that here. And finally, that is the equation of a line which bring that from here to 0. So that is the distribution. Okay, so the only point here was we had a discontinuity in the shear, discontinuity in the bending. Everything else is continuous.
If you look at the horizontal force,
Beg pardon?
what do we have to put a normal graph?
Yeah, normal force is, if I would have plotted that, yeah, this is an easy thing. I thought that was too easy, but you're right. We have to include that one as well.
I mean, the question is asked.
It only that asks. Yeah. So if you would have plotted this would 0 from here to there, and then you had a, I think this is a compressive. Is it? Is it? No, this is tensile. This is tensile. So at the end, it has a non-zero value, and then it becomes to. Sorry. Between here and there, you have an. Yeah, that is, you have 100 Newton only in the fourth zone. In the fourth zone, you have 100 Newton, and everywhere else, the nx is 0. So that is the only non-zero value. All right, I think this is a good problem, this one. Not too many zones, but still it has one shear discontinuity at this end. All right, so this is a cantilever, and the cantilever, we have to find out the reactions. So to find the reaction, first I need to find the resultant of the distributed load. So how do I find the resultant? The resultant is the area of the triangle. So the area is 3 times 2 divided by 2, that is 3 kilonewton. And that 3 kilonewton, the line of action is 1/3 from the base, 2/3 from the apex. So that is correct? And one load is acting here, that is 1.5. And at point A, so let's call this B, call this one A. So I need to have a vertical resistance developing at A. And what else? What is missing here? Bending moment at A, yes. And that bending moment, if this is okay, so AY is equal to 4.5 kilonewton. How do I know that? Simply adding these two numbers, the vertical forces are 0. And then finding M of A. So that is net forces, net rotation with respect to the A equal to 0. And that is 1.5 times 2. That is a positive rotation. Plus 3 times 2 by 3. That's a positive rotation. Pardon? Counterclockwise is positive, and these are, yeah, MA. Well, I mean, that was, I assume MA is in this direction, but if I had this one plotted in the reverse direction, that was minus MA equal to 0. Therefore, MA is equal to 3 plus 2 is 5 kilonewton meter. Is that right? So now that is clockwise. MA is clockwise. Okay, so now I have 5 kilonewton meter here, and AY is 4.5. All right, now we only have one zone, but this is zone number 1, and X is between 0 to 2. Can I ask everyone grab a piece of paper and try to derive an expression for W of X? I give you 5 minutes and derive the expression for that. So I give you a hint. That distribution is a linear, so assume that this is AX plus B. So all you have to do is to calibrate finding A and B. W of x is a distributed load. Intensity of the load, distributed load. So what did you find for the coefficient of A?
3.
That should be minus 3 over 2. Let me tell you why. Anyone else? You got A, Damien? No? So the way to find this is first at x equal to 0, what is W of x at the starting point? That is 0, isn't it? So W of 0, that is equal to 0, which is equal to A times 0 plus B. And from here, I conclude that B is equal to 0. And W at x equal to 2, what is the magnitude? Minus 3. I don't know why everyone makes a mistake. I keep repeating that. That is just for the convenience, you put it at the top. But because those are acting down, that is negative. It's not positive. If you replace that with a resultant load, would you put the resultant load down or up? Yeah. So that is minus 2, minus 3, and that is equal to A times 2 plus 0. And therefore, A becomes minus 3 over 2. And therefore, W of x is minus 3x over 2. Look, this is something promise yourself you won't make a mistake again in this one, all right? So from this point is, sorry? You got negative, did you?
Yeah.
Good on you.
Yeah.
So that means in the first diagram, we have one discontinuity in the shear. Where is the discontinuity in the shear? At the beginning, right? So what is the shear force at this point? I call this point B. Let me call this point B. What is shear at point B? Toby, what is shear force at point B? What do you want? Negative 1.5? Excellent. Minus 1.5. All right? Well done, Tapiva. And then I have to write v of x minus v of b. That is the integral of what? Integral of minus 3x over 2 dx, right? So that is v of x minus 1.5 is plus 1.5 is equal to minus 3 over 4 x squared. Correct? All right. So now that v of x is minus 3 over 4 x squared minus 1.5. If I plug x equal to 0, that gives me 1.5. And if I plug x equal to 2, that is v of a. V of a, that is v at x equal to 2, is minus 3 over 4 times 4 minus 1.5, which is equal to minus 4.5. So that means v of a from here goes quadratically to minus 4.5, correct? And then this is a reverse cup because the coefficient of the quadratic is negative. That's a reverse cup. What do I mean by reverse cup? That is the shape would be like this one. This is minus 4.5. And then I have to find m of x. So m of x minus m of b, that is integral of v of x minus 3 over 4 x2 minus 1.5 dx. So m of b is what? We don't have any bending moment at the beginning, so that is 0, isn't it? So I can write m of b is equal to 0. And now if I plug 0 here, what I get is m of x is minus x cubed over 4 minus 1.5 x, right? All right, let's find out what m is at the beginning. M of b is equal to 0. M of b, that is m at x equal to 0, is equal to 0. M of a, that is m at x equal to 2, that is minus 8 divided by 4 minus 1.5 times 2. So this is 3, that is 2, so that is minus 5. All right, minus 5. So it comes down to so this is a cubic distribution. From 0, it goes to minus 5. And at minus 5, we have a plus 5, which brings that to 0. Okay, in the remaining time, I would like to take you through example of how to calculate moment of area. Okay, so that is problem 681. Let's bring 681. All right, I would like to break that into, this is a compound shape. Compound shape is composed of several primitive shapes. So the primitive shape is used here is a rectangle. I can break that into 3 rectangles. Okay, so that is how I break this one up. That is one shape here, one shape here, and then another one here. Right, so 3 shapes. But these 2 are identical. And because I'm lazy, I'm going to give them the same number. I call this one number 1. This one called again number 1. And this one is called number 2. And then let's take this line as a reference. I take this line as a reference. And how do I find the centroid of the composite shape? So the centroid of the composite shape is y bar is equal to y bar of 1 multiplied by the area of 1 2 times, because this is repeating twice, plus y bar of 2 times area of 2 divided by 2 area of 1 plus area of 2. Do you have any objection? Okay, so that makes 2 times, yeah, the centroid of this shape is 125, and the area of each is 250 times 50, and plus for the second area, what is the centroid of this one? Centroid, the thickness is 50, so the centroid is 25, and the area is 50 times 35 take away 100, that is 250. So that we can simplify, and .7 millimeter. So let's keep things in millimeter, just keep in mind that the calculations are in millimeter. Now, I want to find the moment of inertia, but I know the non-standard moment of inertia with respect to the xx. That is the summation of standard moment of inertia plus the penalty. The penalty is di squared ai. So that makes for 3 of them. So this is 2 times for shape 1. This is a rectangle. I remember a rectangle is 1 over 12 BH3. B is 50 and H is 250 cubed. And the penalty I pay is, the penalty is di. The distance between center of this area and this center is, center of this one is 125. Take away from the centroid is 91.7 squared. And that should be multiplied by the area of this one, which is 250 times 50. Beg pardon? Yeah, that's the area. The last one is the area. 250 times.
No, 125.
125 is the centroid of that rectangle. So that centroid, how much offset it has with respect to the reference point from that of the composite shape. So that is somehow, let me show you. So this area has its own centroid. The centroid is somewhere here. This is for the total shape. This is for the total shape. For that rectangle is here, but that difference, that gap is D1. So D1, we found this to be that difference. Okay, so this is with the first shape, and then I can add this one to that of the second shape, which is plus 1 over 12 for this shape. B is 350 take away 100, that is 250. multiply by 50 cubed, and then the penalty we pay is, that is 91.7 minus 25, because the centroid of this one is 25, and that is D2. This is D2. And the area is 250 times 50. Okay, so if you add all these, that is the moment of inertia for the entire shape. And the unit is millimeter to the power of 4. But this is, I mean, you just visualize how things are. There is one technique called tabular technique. The tabular technique is you make a table. This is more suitable for Excel type of calculation. So you make a table, and in this table you call this A1, Y bar 1, the product of Y bar, these are I. AI and DI and II. Okay, so how many shapes are here? Shape number 1 times 2, shape number 2. So for every item, you put the numbers here, and then you add them up in a tabular way. So that makes the verification of your solution easier. Later on, you want to come back to the calculation. This is less. So let me do one more example here. And then you can do this with the 688. Sorry? The solution for this one? That is in the slide. The slide has it. The slide has the solution. You want to take a photo? Yeah, go ahead. Yeah. But also in the slide, the solution is there.
You want to memorize the inertia for area objects.
For the primitive objects, that comes into the formula sheet.
I remember.
So you need to take note that in the formula sheet, whether they are being given with respect to the bottom line, to the center line. So you have to take that into account, because when it comes to finding the penalty, you need to know how much you use the parallel access theorem. Just as long as you know that my table is giving all the formulas based on the bottom line, based on the center line, then you know how to find out the penalty.
When you put a formula sheet in a rectangle, the rectangle present 1 over 12.
Yes. 1 over 12 is with respect to the center. 1 over 3 is with respect to the bottom. But don't need to memorize it. The formula sheet will tell you which one is which. 688. Okay, so now you have to make a decision how you want to split that into primitive shape. And like I said, there are several ways you can do that. It is just some of the ways are easier than the other ways. You want to make sure you do it in an easy way. So the way I do it is I'm taking this one as shape number 1, primitive shape number 1, and take this one as primitive shape 2. Okay? So first thing, I need to find y bar, and I take my reference from the bottom. That reference is from the bottom. So in the tabular way, you can calculate y bar by writing. So what is the y bar of the first shape? The y bar of the first shape is 2050 plus 25. That is the center of this one multiplied by the area. The area is 50 times 300. That's for the first shape. And for the second shape, what is the y bar of the second shape? 250 with respect to the bottom. The centroid is in the middle. That's 125 plus 125 times the area of this one, which is 250 times 25. And that is divided by the area. So that is 50 times 300 plus 250 times 25. And after the calculation, y bar is almost 2007 millimeter. Now, there are two shapes here. We have to add their moment of inertia, but for each shape, there is a penalty. Okay. So we find everything with respect to the centroid, which is 1/12. So that is I is equal to I1 plus I2, and that is equal to 1/12 BH3. That is, B is 300 and H is 50. And the penalty we pay is how far is the center of this one with respect to here. So that is D1. Which is 275 take away 207 squared multiplied by the area. So that is with the first one. And the second one is again 1/12 BH3. B is 50 and H is 250. Plus, in this case, from that center to this center, the gap is, this is D2. And D2 is 125 take away 207 squared. And the area is what? The area is 50 times 250. Okay. And now if I add them together, the total I is 22 times 10 to the power of 6 millimeter to the power of 4. Okay, so I think that that's enough for today. Just let me finish the attendance, and if you have any questions, I'll take your questions now. You want to Do example from those. You're asking about the, yeah, yeah, Friday, definitely. Remind me and I'll do that for you, right?
I think we have, yeah.
Okay, Martin is here, Damien here, Kapiva here, Leon here, Toby here, and Gabriel here. Okay, questions? All right, do you have any things you want to be changed? I mean, am I going too fast, too slow? Just a style you don't like it, just let me know. That's the best sign.
You did start going fast, yeah, but you kind of got reduced.
Sorry,
You did start going pretty quick in the end.
anything else? That's easy.
Yeah.
Well, yeah, this is mathematics. I know that that's boring, but believe me, if that was easy, everyone was a structural engineer. So you are doing the tough things. Hopefully, you get the credit for it. So just if you find a different way of learning which make things more useful for you, just let me know. I'm happy to try it. All right. Okay. Looking forward to see you Friday. Thank you very much.
Thank you, sir.
Thank you.